Today, we are going to explore a fascinating problem from number theory involving the Markov equation. Our objective is to find all triples of positive integers x, y, and z that satisfy the equation x squared plus y squared plus z squared equals 3xyz. Our goal for this session is to understand the structure of the solutions to this equation and learn a technique called Vieta Jumping to find them. The Markov equation itself is written as x squared plus y squared plus z squared equals 3xyz. This equation is famous because it looks like a simple quadratic at first glance, but it hides a deep branching structure of solutions that can be visualized as a tree. Let's start with the most basic solution. If we let x, y, and z all equal 1, we get 1 squared plus 1 squared plus 1 squared, which is 3. On the right side, we have 3 times 1 times 1 times 1, which is also 3. So, the triple 1, 1, 1 is our fundamental starting point. Now that we have our first solution, let us see if we can find others. A powerful method for this is called Vieta Jumping, or root flipping. Our goal is to use Vieta Jumping to generate new solutions from known ones. Suppose we have a solution triple, x, y, and z. Let's treat two of these, say y and z, as constants and view the equation as a quadratic in terms of x. If we rearrange the Markov equation, we get x squared minus 3yz times x plus the quantity y squared plus z squared equals 0. From the theory of quadratic equations, specifically Vieta's formulas, we know that if x is a root of this quadratic, there is a second root, let's call it x prime. The sum of the roots must be equal to 3yz. Therefore, we can find a new value, x prime, by calculating 3yz minus x. This means that if xyz is a solution, then x prime yz is also a solution. This process allows us to jump from one solution to another. Let's apply this Vieta jumping technique to our starting solution, the triple 1, 1, 1, to see where it leads us. We start with our fundamental solution, 1, 1, 1. Let's fix two of the ones and find a new value for the third, using our formula x prime equals 3 times 1 times 1 minus 1. This gives us a new solution triple, 1, 1, 2. As you can see, 6 equals 6, so the triple 1, 1, 2 works. Now, let's keep going. We have 1, 1, 2. If we flip one of the ones, we just go back to our previous solution. So, let's keep the 1 and the 2 fixed and find a new value for the other one. X prime equals 6 minus 1, which is 5. This gives us the triple, 1, 2, 5. It works again. Sum of squares is 30, and 3 times 1 times 2 times 5 is 30. From 1, 2, 5, we could fix 2 and 5 to find a third value. 3 times 2 times 5 minus 1, which is 29. Each jump produces larger and larger integers, and by swapping which variables we hold constant, we can branch out into infinitely many solutions. To visualize how these solutions grow, we can organize them into what is known as the Markov Tree. Imagine the solution 1, 1, 2 as the root of our tree. Each triple can branch into 3 possible neighbors by applying the Vieta jump to each of its 3 coordinates. Branch 1, 1, 2, 5, which comes from 3 times 1 times 2 minus 1. Branch 2, 1, 5, 13, which comes from 3 times 1 times 5 minus 2. And branch 3, 2, 5, 29, which comes from 3 times 2 times 5 minus 1. Notice that one jump always takes us to a smaller solution, while the other 2 jumps take us to larger solutions. This means that every single positive integer solution to the Markov equation can be reached by starting at 1, 1, 1, and moving along these branches. The numbers that appear in these triples, 1, 2, 5, 13, 20, 9, and so on, are called Markov numbers. They appear in many different areas of mathematics, including the study of how well irrational numbers can be approximated by fractions. To summarize, first we started with the basic solution 1, 1, 1. Then we used Vieta jumping to find new coordinates. Finally, we discovered an infinite tree of solutions. By mastering this root flipping technique, you can find as many solutions to this complex-looking equation as you like.